Hello everyone. So today is day 5 of our challenge of solving 30 deep learning projects in 30 days. So let's see what the problem is about. So it says the problem is to experiment with optimizers. So we have been so earlier we saw experimented with activation functions, then before that we experimented with learning rates. We implemented couple of I mean solved couple of problems using sequential model. So today we are going to experiment with the optimizers. So far we have used only Adam, but today we are going to use SGD and RMSprop as well. So let's do let's do it. The code flow is going to be same. We will go take the help from ChatGPT, and yeah, let's start. Here it is day 5, and here is the problem statement. There is an extra space. So let's wait for the ChatGPT to generate the response, and then we will start. Okay. Okay. So if you remember, or if you would have been following my past 4 posts or videos, you know that there we have been experimenting with MNIST dataset. Today we will be exploring CIFAR dataset. This is going to be a new one. So let's start. The ChatGPT says that optimizers is crucial. So because they control how a neural network updates its weights to minimize the loss and the find the best solution. For today's task, we will use a pre-built convolutional neural network (CNN) on the CIFAR-10 dataset. Compare the impact of three popular optimizers: SGD, ADAM, and RMSprop. So there are a couple of, three things that we have never heard before. At least I have never heard before. A pre-built convolutional neural network, and then CIFAR-10 database, and then two more optimizers, which are SGD and RMSprop. So let's overview the problem. The problem is that the CIFAR-10 dataset contains 60,000 color images across 10 categories. So we have 60,000 color images across 10 categories, and the categories are like this: car, birds, airplanes, etc. We will use a pre-built convolutional neural network architecture to train on this dataset. Okay, we will experiment with the three optimizers. First is SGD, which is stochastic gradient descent. Second is Adam, which is adaptive moment estimation, and the third one is RMSprop, which is root mean square propagation. Okay, so the brief overview of the optimizers is that SGD, the basic optimizer that updates weights using a small step controlled by the learning state rate. Okay, can be slow, get stuck. By adding momentum, can help it more. Okay, so it updates the weights by a small step, and they are being controlled by the learning rate. I don't know how. Maybe we need to ask ChatGPT again to simplify it and explain it with the help of example. Adam. Adam is adaptive optimizer that adjusts the learning rate of each for each parameter using estimates of the first and second moments of the gradient. Okay, that adjusts the learning rate for each parameter using the estimates. I don't understand. So it adjusts the learning, adjusts the learning rate for each parameter using the estimates of first and second moments. We need to, I guess I need further clarification from ChatGPT. It combines the benefits of SGD and RMSprop and is often a go-to choice because of its efficient learning. Okay, that's why we have been using this one only. It says that RMSprop is similar to Adam. It adjusts learning rates based on recent gradient, focusing on stabilizing training, particularly useful for deep neural network. Okay. Before we go and start coding, what should we do? I should ask ChatGPT to help me understand these with the help of easy example without going deep in the terms and maths. So I'll go. Can you? I have not understood much about the optimizers. Can you please explain them with the help of easy examples? So let's wait for it to generate. I guess it has generating. Okay, so let's start understanding. The first one is, what are optimizers? Optimizers are like guides that help your neural network find the best solutions. Remember, whenever we were specifying writing the code here, if I go here, uh, uh, just a second here, you see, whenever we were defining compiling the model, we used to specify the let's go to the basic one. We used to specify the optimizer, right? And along with that, we do specify the loss and metrics, as in how to calculate the loss and also how to calculate the performance. Optimizers, they do what? Let me close it because it is creating a lot of confusion. So optimizer, they do what? They help. They are like guides that help your network find the best solution. So imagine your neural network is a hiker trying to find the lowest point in hilly landscape. Here, what it is doing, trying to say with this lowest point in a hilly landscape sentence, it is saying that we need to find the minimum loss. The minimum the loss is, the better the performance of our model is. Okay, so the optimizer is the strategy or tool the hiker uses to get to the lowest point. Okay, optimizer is the strategy the hiker uses to get to the lowest point as quickly and efficiently as possible. Understood. The first optimizer is SGD, stochastic gradient descent. It says the analogy is that a hiker taking small steps down a hill. Okay, a hiker is taking small steps down a hill. Imagine you're a hiker trying to reach the lowest point in a valley. You can only see the part of the hill right around you, and you take steps downward in the direction that looks like it leads lower. Okay, with SGD, each step is like taking a small careful move down the hill based on the current slope you feel under your feet. Okay, so let's say we have a, let's say, draw dot I io. Okay, and let me do what, is there any free pointer? Okay, so we can use this one. So, oh, nice. This is looking nice. So see, there is a slope. There is a slope. Now, what SGD is trying to do, it is taking steps, slow. I mean, very small steps, going in the direction where it looks like that it is going to achieve minimum loss, and then it is taking small steps, taking small steps. In the reference of hiker example, the hiker is going in the direction of where it sees that the hill is going downward, and it is taking small steps with the hope that it is going in the direction with the, I mean, with the minimum height, or with in terms of neural network, SGD goes in the direction where it thinks that the loss is slowly decreasing, taking small steps. So with SGD, each step is taking like small, very careful down the hill based on the current slope you feel under your feet. Characteristics of SGD: careful steps. You only take steps based on local information. If the ground feels like it is sloping down, you take a step that way. Yes, correct. If I, for example, if I'm on this, if I feel that the slope is going down, I'll take step towards it. I don't care whether this path is going to lead in the wrong direction. I mean it will increase for in future, but if it is decreasing, I'll opt this thing. Because you're taking small steps, sometimes relying on what is directly around you, you may not always find the fastest path down. Slow progress. Makes sense. Momentum. You can improve SGD by adding momentum, which is like letting the hiker pick up some speed when going downhill. Okay, momentum helps with that. This helps you avoid getting stuck on small bumps and can lead you more directly to the lowest point. Let's read it again. This helps you avoid getting stuck. That is why we are going ahead with smallest momentum on small bumps and can lead you more directly to the slowest point. Okay, momentum. In neural network, it says that the SGD works by adjusting each parameter, that is weight, a little bit at a time in the direction that reduces error. It's straightforward but can be slow, especially when dealing with complex landscape where there are lots of ups and downs. Okay, so it is slow, reduces, it goes in the direction where it sees that the error is reducing, and it goes like takes little bit, I mean, adjusts parameters like weight a little bit at a time. Then we have Adam, which is adaptive moment estimation. Simple analogy is that a hiker with adaptive gear and memory. Okay, now the hiker has what? Adaptive gear and memory. Imagine the same hiker, but this time you are equipped with some special gear. Okay, you have boots and that can adjust based on how steep the terrain is. So now the hiker has adaptive gears and memory. In the adaptive gears, let's say hiker has good boots that are hiking boots. Now the hiker also has a notebook to remember the direction that the hiker has already tried. So they have memory, which is like notebook to note down what path the hiker has already, I mean, opted for. And hiker also has gears that are good for hiking, like the boots, hiking boots. Now, characteristics of Adam is that it is adaptive steps and memory. Adaptive steps, that means the boots can adjust their step size based on how steep the slope is. If it is a gentle slope, they take larger step. If it is steep, they take smaller. So with here the adaptive steps or adaptive boots they mean that they automatically adjust. For example, if it is a gentle slope, they take larger steps. If it is a smaller, if a steep slope, they'll take smaller steps. And in terms of memory, the notebook helps the hiker remember the direction they have already tried. If the hiker notices that the hiker has been leading heading downhill steadily, you keep going in the direction with more confidence. The hiker will go in the will keep going hiker will keep going in the direction with more confidence, with the help of memory, with the help of notebook. Now in terms of neural network, what it means, Adam combines the advantage of momentum, like remembering what you're going, and adaptive learning. So momentum as in it the Adam takes the advantage of the memory and the adaptive steps. Adaptive steps means adaptive learning rates, like adjusting the. So Adam does what? It adjusts the learning rates. It is a smaller, smart hiker that adapts based on the terrain, making it both fast and effective. That's why Adam is one of the favorite choice of for training. It adjusts well, speeds up when it is safe, and slows down when it needs to be careful. So why Adam is good? Adam is good because why Adam is one of the favorite choice for training, because it adapts the learning rate based on the whether based on the terrain, which is making it faster and effective both. And it takes the advantage of the momentum, as in remembering where it has I mean where it is going. Now RMSprop, which means root mean square propagation, which is root mean square propagation. Simple analogy is that a hiker with shock absorber to smooth the descent. So imagine the hiker again, but this time with shock absorbing shoes. Those shoes help you move steadily downhill without bouncing too much, even when the terrain gets a bit rocky. RMS prop is all about keeping the journey smooth, preventing big jumps that could lead you in the wrong direction. So it is. I do understand that, but let's understand it with the help of in the neural network. In the neural network, RMS prop adjusts the step size based on the recent activities. So what it does, it adjusts the step size. That is maybe the learning rate based on the recent history. It is especially useful when the terrain, which is the lost landscape. This terrain is like lost landscape, is bumpy, which often happens in deep learning neural network. It helps ensure that the steps are not too big, preventing the network from missing the optimum point. So what it does, we do understand this RMS is like Adam, but the difference is that it has shock absorbers, which means it takes the advantage of the history data, and based on that it decides the step size. And it is also not too big so that it does not miss the optimum point. Um, Now skipping the hiker analogy, let's go to the this thing that when to use which optimizer. SGD is best for simpler tasks when you want to come. So SGD is really simple. The hiker is alone, has no gears, has no notebook, has nothing, no shock absorber shoes, nothing. So SGD is just taking smaller steps, going in the direction where based on the local data, uh, going in the direction of minimum loss, optimizing loss. So it is usually good for the simpler tasks when you want more control over the learning process. Works well when combined with momentum, which is memory. Good if you don't need adaptive learning and have a good learning rate already. Adam is The most popular choice, yes, we have used it for many deep learning problems. Works well for almost all use cases, particularly when training deep networks. Okay, it is fast because it has a notebook, which is a momentum to remember the directions, and also it decides the step size, and it can and the step sizes they changes based on the bumps and the terrain. Similar to Adam, RMSprop is also a great optimizer for complex deep network where the terrain is uncertain. Correct. It is a good choice when you need steady training without large jumps. Yes. So the main difference between Adam and RMS, they are identical, but the difference is that when we need steady training, when we do not want to miss a point, an optimum point because of big jumps, then we go ahead with RMS prop. Otherwise, we go ahead with Adam. Okay. So let's go back. We have understood them. We have understood about the optimizers that we are going to explore today. Let's go and start coding. What we will be doing is we will load the CIFAR data. Here it is not sharing about. I mean, here it is not using pandas to see how the data looks like, but we will use it. Then we will build the SCNN convolution pre-build convolutional neural network model. Then we are going to use the three optimizers SGD, Adam, and RMSprop, and then compare the performance. So let's come to the pie chart. Close already coded problems. Create a new file called day5.py. Add it to the Git repository. Mention the problem statement. The problem statement is that we are experimenting with the optimizers today. Okay, so let's start. So we are going to import. What are we going to import? TensorFlow as TF. From TensorFlow Keras dot datasets import CIFAR-10. That yes. From TensorFlow Keras dot layers, not layers, models, import sequential model. From TensorFlow Keras layers, import dense. I guess flatten the images. They are neural network expects the input in 1D, one dimensional vector. So we have to flatten the images. And then today we will be importing two more layers, convolutional 2D and max pooling 2D. So it is convolutional 2D and max pooling 2D. Then we will import matplot library dot pyplot as plt to plot the graph to see the performance and accuracy of the models. Now let's do what? Load the data. Here we are loading x train, y train. Just give me a second. Then we have x validation, y validation, and then we are going to use SIFAR dot 10 SIFAR 10 dot load the data. Um, data set. Now we are going to not. So if you see the data is usually, let's do what? I want you to see the data. So for that we are going to convert it into data frame. And for that we will have to import the panda library. So visualize, not visualize. Let's understand the data. So for understanding the data, what we want, we will use create a xtrain dot data frame panda dot create a data frame out of this x train. Okay, print xtrain data frame dot head. Let's do what, run this line, this file, sorry. And we have error. It says that the shape of this, what is the shape, the shape of this exchange is 50,000. And let's do what, let's not do this, let's see the shape. Print x train dot shape, print x validation dot shape, print x not x y train dot shape. Then we will print y not y validation dot shape. Let's run it and see the dimensions of the data set. For training we have 50,000, for validation we have kept 10,000 images. Similarly, for the target, 50,000 for training and 10,000 for validation. The image size is 32 by 32, so we'll have to flatten it. That is why we were not able to see convert it into data frame. So first we will flatten, normalize the images. Usually the images are in the range of 0 to 255. So we have to normalize it so that the model, we will be able to train our model better. I mean faster actually. So normalize the image, so normalize pixel values between 0 to 1. So for that we will be doing, let's comment this, we saw how the data looks like. So for that we will do x train. Here you would see that it is only one dimensional vector, so we do not have to, I mean it talks about what category the data is of, so we do not have to do what, we do not have to convert it, sorry, normalize it. So x train will become x train divided by 255.0, x validation becomes x validation divided by 255.0. Yes. Now we will do what, I'll show you. It is, I'll understand the data, so I'll say series, we will see x not y train, y, we'll simply use this data frame. Okay, clear it. Y train panda dot series, label. Let's print it, data frame, y train data frame. Okay, so The first row is of six category. The second row is of nine, nine, four, one, two, six, nine, nine. So these are the categories. Okay. Now let's do what? Let's do what? Flatten it. Just let's flatten the exchange. We do see that the target looks like this, but in order to see training, the features, the images, we need to flatten them first. Why? Because the data frame does not expect, because of this error. It should be a 2D error, and it was not 2D error. So what we are going to do, flatten it, x frame flat. So we'll do what? uh, how do we flatten it? I forgot. uh, just a second. How did we flatten it? Like on the, yes, we reshaped it. So we did, I'll use x train dot reshape -1. And what was the size originally? The size was 32, 32, 32 multiplied by 32. Let's print x train flat dot shape. Let's run it. And it is 15,000 images. Okay. How do I reshape? How do I need to see them as data frame before proceeding. No, the data set actually. So I want to see the CIFAR-10 dataset as data frame. So yeah, we need to reshape it. Okay, just the shape is 32 multiplied by 32 multiplied by 3. So it is going to be multiplied by 3. So let's do this. Now we have 50,000 and then we have this much. Now if we are going to see them as data frame, x frame, not this is flattened and this is data frame, then we will have to do pass this x train data frame. And then let's see this x train data frame. So I was passing the wrong dimensions here, and this is how the data looks like. And if I don't normalize it, let's see how the data would look like. See, the data looks like in uh, range 0 to 255. Now we are normalizing it in the range of 0 to 1, so that our model, we will be able to train our model faster. See. Okay. So in how many columns do we have? 3062, 306, sorry, 72, which is 32 by 32, 32 into 32 into 3. So 0 to 3071, correct. And if I want to reshape x, not x, the y train flat, I'll say x y train dot reshape -1. I'll say, what was the original shape? If we remember, the original shape was 1 only, right? Okay, so yeah, it is already in one. I was doing it correctly, but now if you want to show it in the form of series, what do we have to do? Uh, for y train flat, what do we have to do? We have to reshape it. Do we have to reshape it? No, we do not have to reshape it. What do we have to do? Data frame. Creating the data frame, what do we have to do? We have to use the series, because for series, like for one dimensional, we use series. Here we go with this y train dot, not reshape, flat. It will flat that 50,000 into 1, and then the name is going to be label, and then we will print this y train data frame, and here we will print the head. First five will should be enough. Let's clear it and run it. So this is how our training data looks like, and this is how our validation data, sorry, the target looks like. So yes, we now see how the data looks like. So we will comment it. Now we will do what? We will, instead of flattening it right here, because again the neural network understands 1D array, we will flatten it as a layer in the model itself. So we'll come back to the original code. So yeah, yes, we have flattened it. So we will build a function called build CNN, which is to build the model. Um, and why we are adding this convolutional 2D layer with ReLU activation to extract the features from. So we will not go in depth for this, because we have separate individual problems to understand the CNN model. Today we will just go and use it, which is and just touch the surface. So this convolutional 2D layer is added with the activation function ReLU, which is rectified linear unit, and this is we add to extract the features from the images. We extract the features from the images. Then we have max pooling 2D. It reduces the dimensions of the feature image maps. We will understand that also in the coming videos. So we add that. So let's go ahead with this, that this convolutional 2D layer we add to extract the features from the images. Now we want to reduce the features of the extracted features from the images uh, to 2 by 2 dimensions. So that is why we are using this max pooling 2D. uh, this is clearly mentioned in the Kaggle convolutional neural network course that I have told you to go and visit once before starting this challenge. So this is also mentioned here, explained clearly. But we will come back to this topic and understand this in depth. But for now, this is to reduce the dimensions of the extracted features, and this is to extract the features from the images. So let's build the function for what? For building our CNN model. So build the CNN model. Define the function to do what? Build the CNN model. So we'll say def build CNN, and then we will do model. It is a sequential model, and we will add layers. First layers is going to be convolutional 2D layer, and here we mention this, how many neurons we want. We want 32 images, and the size of the images are 3 by 3, and Okay, then we have the kernel size is 3 by 3, filters are 32. Then we have activation, not here. Activation is going to be rectified linear unit. Then we have input shape is going to be what? 32 by 32 into 3. We saw it, like we you remember that we saw the shape here. This was the shape. Now we'll come here and then we add a max pooling 2D. Now we are going to uh, reshape this extracted feature into 2 by 2 dimensions. Then we will add one more convolutional layer, a 2D layer. Here the size is going to be 64 neurons, and then we will define the kernel size, and the activation function is going to be rectified linear unit. Again, we will not go in deep about these layers because I don't want you as well as myself to become to be overwhelmed with this new topic, which is an advanced one. We will come back to this one in the week 2 and explore this CN convolutional models in depth. Now once done, we will add one more layer. So here add convolutional 2D layer. The size is 64, and the kernel size is 3 by 3. If you see the CNN, not this CNN model looks like grid. So they look like this. So here we need to specify the kernel size. We say that it is going to be 3 by 3. So this is how it is mapping. This is 3 column 3 column. This is how it is mapping. This is how it is mapping. So that is why we mentioned that the size. And then we reduce that size to 2. Now once done, come back to this thing, and the activation function here we are using is rectified linear unit. Once done, we will flatten this image to flatten this image because the model, the dense layer, understands only 1D actor, sorry, 1D vector. So now we'll go with 64 neurons. Activation function is rectified linear unit. Then we'll have our final layer for the generating the output, which is to generate the probability of an image to be out of these 10 categories. So we need to specify 10 as the 10 neurons to show 10 categories. And the activation function we need is softmax. We use it because softmax it it does what? It generates the output of the neurons in the form of probability, such that the sum of the probability of these 10 neurons is going to be 1, and at the end whichever neuron is going to have the highest probability will be our answer. So we are done. We need to return it though. Return model 1. We are done with it. It says that we need to have two spaces, not here. Done. Now we'll come back to this thing. Now we will train the model with different optimizers. Train the model with different opti. Okay. So let's create list of optimizers, which is optimizers, which is first one is SGD, and this is, let's import them one by one. Import Terrace from TensorFlow Keras optimizers. Import SGD Adam, and then what do you want to import? RMS root mean square propagation. And here the SGD, here we mentioned the learning rate as 0.01. We saw that this is actually a good rate in our day 3 video. The momentum is going to be 0.9. Then we will have Adam as Adam. The learning rate is going to be 0.001. Learning rate is 0.001. We want it to be a little slow. Then we'll have RMS propagation, and here we'll have RMS propagation. The learning rate is going to be same, 0.001. 0.001. Yes, we are almost done. Let's come back here. Optimizers. Let's create a dictionary to store the training and training history with, okay, there is a typo, training history. Now I'll do what? History dictionary. Okay, so we'll go to our optimizers. In optimizers, we will uh, build the model. Mention this optimizer, so sorry, for name optimizer name, and here it is going to be the optimizer. In optimizers, the optimizer name we will pass here. No, this is going to be the optimizer. Where do we mention the optimizer? We can build the model without the optimizer, right? Now we will compile the model.compile. Here we mention the optimizer as optimizer optimizer. The loss function is going to be what? Sparse categorical cross entropy. Why? Because we are predicting for a category which are digits, so that is why it is sparse categorical cross entropy. Then we have metrics, and metrics we will predict using the, we will calculate the performance using the accuracy. Now once done, we do what? We will print a message so that it becomes easier for us to see. Training for, let's wait a second, training for optimizer name, and now we will train model dot fit, and here we mention what? X train, X Y train. Validation data is not here. Let's do this way. X train, Y train. Validation data is X validation, Y validation. Epochs are going to be 10. That is how many iterations we want through entire data 10. Then in each iteration we want the batch size to be 32. We want to see the output while in the terminal while it is the training? Yes, so we mentioned 1. And let's store this history of this model training in this history variable, and this then update it in the history dictionary with the optimizer name, this history dot history. Now we have successfully trained. Now let's visualize the of the loss and accuracy with different optimizers. So we'll do what? We will do what? We will plot a graph, and the size is going to be 14 is to 8. Now we will iterate to all the optimizer names. So it is going to optimizer name in optimizer name in optimizers, and we will do what? Plot, not from, I have a typo, for plot. We will plot history dot, not, yes, history dictionary dot optimizer name, plot the loss for our training data, and the label is going to be training law. There is a typo, training loss for optimizer. This optimizer, this is the training loss. Then we will plot the history dictionary of this optimizer, and plot the validation loss. Not lambda. Label is going to be validation loss for optimizer name. And once done, we will do what? The X label, mention the X label of the plot, which is going to be box, and the Y label is going to be loss. The title of the graph is going to be training and validation loss with different optimizers. Now we want to see which line represents what with the help of this legend function, and then we will simply show, not show it right here, show it later. Yeah, we will show. Let's show. And we will do what? Copy it, and now we will do what? Visualize accuracy. For now we visualize accuracy. Earlier we visualized loss. Visualize, we'll say plot loss. Now we will plot accuracy. Everything is going to be same, but now in place of accuracy validation, we will see the accuracy. Here it is accuracy, and I do have a typo, and accuracy. So here I again have a typo, it is bell loss, not validation. Let me capitalize it. Now done, we are pretty much done with our coding. Let's go and run this program and see how the model performs with different optimizers. But before that, we have an error at line number 54. So we have, okay, so here it should be items, and that now it should run. Yes, it is running now. So it is training the SGD, training for the SGD optimizer. So here we have specified it to go for 10 epochs. See, it is taking time. Each epoch is taking 13 seconds around. We will see, we saw that it is a little slower because it takes small steps. Now let's wait for how it performs with the atom. Usually with the atom it runs faster. So yes, let's wait for it and see how it is performing, going to perform for the atom. See, it is taking each iteration, this epoch is taking around 15 seconds. We are almost at the end of our training with SGD optimizer. Yes, it started with accuracy 0.37 too low, ending with 0.76, 0.78 maybe, and will end around 80, 90 accuracy. So it is, the accuracy is gradually increasing. The loss is also gradually decreasing. Started with 1.6, ending at around um, 0.5 ish, 5.6 C. So for validation also, it started with the loss of 1.3. It is ending at uh, 1.09. So it decreases, was decreasing, and then it increased. It was decreasing and then it got increased. So there are few bumps here that we have encountered. For validation accuracy also started with 0.59, and then the accuracy is increasing and closed at 0.67. So we do see some bumps in case of validation the unseen data. But yeah, it took some time. And see here, um, so it was taking 16 seconds, 15 seconds, 13 seconds. So it was taking this much time. For our in case of Adam, it is taking a static of 13 seconds. But let's wait because this time got changed around for our fifth epoch. So let's wait for it to see how it is going to perform for the fifth, sixth, seventh, eighth, five epochs, five onwards. So for the fifth epoch, it took 13 seconds. It is taking, like, see, that is taking too much. It is taking 10 milliseconds for each step. Here it is taking 8 milliseconds for each step. So really good. It is comparatively faster. With loss it started with 1.5, and here it started with 1.6, so it was loss. This is also good. In case of Adam, the accuracy was started with 0.1 45%, and I guess it may close at 79 or 80, more than that. For validation, if loss, it started with 1.3 and it may end at like it is decreasing gradually, which is really good. The accuracy should be steady. So the accuracy for unseen data started with 0.5, 53%, 60, 65, 67, and it is gradually increasing only. See, it is gradually increasing only. So there is some steadiness in case of Adam. The accuracy got close at 77%. Here the accuracy was more, it got close at 79%. But there was more steadiness here. There is more steadiness in case of Adam. On an average, it took 8 milliseconds to for each step, so it was faster. Now, if we come to the RMS prop, the logic how I'm going ahead deciding which one is good for me is that the loss should be minimum and steady. The accuracy should increase and it should also be steady, and it should reach the maximum accuracy faster and effectively. So here we see it is also taking comparatively less or equal amount of time as of Adam. The accuracy, the loss is also decreasing for the training as well as for the validation data. The accuracy is steadily increasing, and by the sixth only it reached 74%, which is really good. The validation accuracy is also slowly increasing. So let's wait for it to generate all the rest of the three epochs. So then we will have some clear understanding. Okay. So it has generated the response, but let's wait. So it took like on an average 8 milliseconds, which is similar to the Adam. The loss started with 1.5 and closed at 0.55. The accuracy is the maximum in the case of propagation. The validation loss is gradually decreasing only, but then after the fifth epoch it increased and then reached around the same where it started, like the second epoch, which is bad. Then there is accuracy which is slowly increasing and steadily increasing. So the accuracy is really good in case of RMS proposition, but there is some loss increasing and then further it increasing decreasing and then further increasing in case of unseen validation data. So now let's come and understand the graph. So this is the loss. So let's see the loss for the SGD optimizer. It is the blue one and orange one. Blue one on orange one. Blue one is like this. It is loss is decreasing, and orange one is decreasing, and then increase, decreasing. And then for Adam, it is green and red. Green, it is decreasing, and then so it quickly dropped, so the accuracy quickly see the loss quickly dropped in case of Adam, and the validation is red, so we will go, it is decreasing only, and then there is slight bump. So this is more steady than the SGD. For the RMS prop, the training and validation looks like violet, dark and light, violet, and this is violet. So if we see it further got decrease, I mean there is better jump in the loss. It decreased way further than the Adam. Here this is the graph, and then it is going like this. So the loss is here, I mean even further minimum than the Adam. But there is there the for the validation, it is not as good as with for the Adam. See, there are bumps here, and it increased like too much here. So this is the loss metric, and now for accuracy we see that the accuracy should increase. For training and validation training like this, it is increasing. There is huge change, drastic change after at the first epoch, and then slowly steadily increasing. Then the validation there is increasing, then increasing, and then steadily increasing, and then decreasing, and then increase, and then there is stagnancy. For the atom, there is green and red lines. Green, there is increasing, and then it quickly reaches the accuracy. This is better. And then the red one, there is increase in the unseen data. Then there is decrease. Then there is increase, and then there is slight decrease. So for validation, RMS is, I guess, better performing. So let's see actually. For now, till now, Adam is better performing because the bumps in Adams are relatively lower and very smaller than the bumps in the SGD validation accuracy curve. Now for the curve for the RMS propagation, it is represented by this color and this color, violet. So this color and this color. So the for the training data, the accuracy is increasing, and then it increase further. So the accuracy is better for RMS uh, out of all these three optimizers, but the for the validation data, it decrease, and then there are more bumps here. So for unseen data, the accuracy is has more bumps than the atoms. So the steadiness is there for both the validation and the training data. So let me take a screenshot here so that even if we lost it, we can come back to this. Now let's see what the uh, chat GPT would say here. Yes, see, SGD was slower, especially with momentum, and can struggle with more complex data. Adam frequently go to the optimizer for is frequently the go to optimizer for neural network model. Yes, it has faster convergence, stable learning. Adam, yes, and it has higher validation accuracy. Yes, it was quickly convergence. Yes, we saw that for RMS propping, and the performance also is steady. But here for Adam was more steady, and it takes longer time. Yes, out of the three, SGD was the slowest one, and also we did not see it that stable. It was less stable out of the other three, out of the three optimizers, the SGD one. So yes, we seem to have solved today's challenge. So let's go and commit this thing at day 5. Let's commit it, add code for day 5. Let's push it to the main branch, and let's go and see this code, and we do see the code. So yes, now you should be, by the end of the week you should see the progress post or the textual representation of how we have solved and everything on this tech journal. And you should soon see whatever we have recorded, however we have coded it in the video form on the YouTube channel. So thank you very much.